Greetings and welcome back, to the second video in the series for trend lines and regression analysis. In this particular video, we are going to look into simple linear regression. Regression analysis is a tool for building mathematical and statistical models that characterize relationships between a dependent ratio variable and one or more independent or explanatory variables. They are either ratio or categorical, all of which are numerical. So we have to go back, all the way to chapter 1 to where we actually talk about the four different types of variables. We have nominal, ordinal, interval, as well as ratio. So categorical is the nominal variables. So there are two types of regression. We have simple linear regression involving a single independent variable, and we have multiple regression involving two or more independent variables. Simple linear regression involves finding a linear relationship between one independent variable x and one independent variable y. The relationship between two variables can assume many forms, such as illustrated in the plots below here. So we would expect to see data line up perfectly along a straight line. If we want to verify that generally the relationship is linear. If the relationship is non-linear, then alternative approaches must be used, and if the relationship evidently shows that there are no relationship between the two variables, then it is pointless to even consider wanting to develop a linear regression model. So for example, we can use, we want to look at if there are any relationship between the size of a house and its market value. So when we plot, if we look at the variable, we have on the x-axis the square feet of the house, and in the y-axis we have the market value. So here we are using the scatter diagram to investigate if there is a relationship between market value and the size of the house. So looking at this, this scatter plot of the full data set of 42 homes indicate to us, that there is a linear trend, whereby we can see that a higher market value, are generally associated with larger home size. And therefore, we can conclude that simple linear regression would be an appropriate technique for predicting market value based on the house size. So, once we can use the best fitting regression line in order to express the relationship between the dependent and independent variables by using a single linear equation. Where we will be able to express market value equals to A plus B multiplied by square feet, where A is the y-intercept and B is the slope of the line. If we draw a straight line through the data, some of the points will fall above the line and some will fall below it, and perhaps a few of the data will be on the line itself. This figure here shows that there are two possible straight lines that can be drawn to pass through the data. Line A and line B. Line A is clearly a better fit to the data, because all the points are closer to the line and the line appears to be in the middle of the data set that we have. The difference between the lines is in the value of the slope and the intercept, and therefore we seek to determine the values of the slope and intercept that will provide the best fitting line. Okay, if we look back at the example of the house, okay, we can see here, okay, that we have an equation market value equals to 32,673 plus 35.036 multiplied with the square feet. Okay, if let's say we have okay, a home that is of 2,200 square feet, we want to find out what is the estimated market value. Then we substitute 2,200 into the market value equation here, and we estimate that, okay, a home with a size of 2,200 square feet is approximately $109,752. So we can use, okay, this equation in order to predict different home sizes. So let's say if you want to find out what is the estimated value for a home with 1,500 square feet, then substitute 1,500 into the market value equation so that you can get that, you can find out what is the market value for that house. The regression model explains the differences in market value as a function of the house size, okay, and provides better estimates than simply using the average of the sample data. One important caution is that it is dangerous to extrapolate, okay, a regression model outside of the ranges covered by the observations. Okay, so in this case, the observation is roughly up to about 2,400 square feet. So therefore, okay, we should not use this model to predict for a house that is, let's say, 3,000 square feet in size. The mathematical basis for the best fitting regression line is called the least squares regression. Okay, in regression analysis, we assume that the values of the dependent variable y in the sample data are drawn from some unknown population for each value of the independent variable x. Okay, simple linear regression model can be found using the formula y equals to beta naught plus beta 1 multiplied with x plus epsilon, okay, where epsilon is the general error term, okay, to the mean value. However, because we do not know the entire population, we do not know the true values of beta naught and beta 1. So in practice, we must estimate these as best as we can from sample data. Therefore, again, we define B naught and B1 to be the estimates of beta naught and beta 1. Thus, the estimated simple linear regression equation is given by y hat equals to b naught plus b1 x. Okay, and let xi be the value of the independent variable of the ith observation. When the value of the independent variable is xi, then yi equals to b naught plus b1 xi is the estimated value of y for x of I. One way to quantify the relationship between each point and estimated regression equation is to measure the vertical distance between them. Okay, as we can see here in this particular graph. We can think of these differences, okay, as the observed errors, often called the residuals, associated with estimating the value of the dependent variable using the regression line. Therefore, error associated with the ith observation can be found using this formula. Error of I equals to y of I minus y hat of I. The best fitting line, okay, should minimize some measure of these errors. Because some errors will be negative and others positive, we will have to take the absolute value or simply square them. Okay, as we can see in this particular formula. If we can find the best values of the slope and intercept that minimize the sum of squares, okay, hence the name least squares of the observed errors, we will have found the best fitting regression line. Okay, please don't worry about calculation. I am sharing with you the formula so that you're aware of it, okay, but you will not need to know how to calculate in this particular course. Okay, let's look at some regression statistics. Okay, terms that you will need to know. Multiple R is another name for the sample correlation coefficient. Okay, R. The values of R varies from -1 to +1. Okay, R is negative, okay, if the slope is negative. So a value less than 0 indicates negative correlation. A value of positive interpret as a positive correlation. The greater the number is to 1, the more correlated it will be. And if the value is 0, then it indicates that there are no correlation. R square is called the coefficient of determination. Okay, it is a measure of how well the regression line fit to the data. Okay, varies from 0, no fit, to a perfect fit. Then you get your R square equals to 1. Then we have adjusted R square. Okay, it is a statistic that modifies the value of R square by incorporating the sample size and the number of explanatory variables in the model. Okay, this will be useful when we are comparing one model with another model. Okay, and we will look at the adjusted R square more deeper when we talk about multiple linear regression later. Okay, the last regression statistics term is the standard error, which is the variability of the observed and predicted Y values. Okay, this is formally called the standard error of estimate. So if the data are clustered close to the regression line, then the standard error will be small. Okay, the more scattered the data are, the larger the standard error will be. So let's look at an example here. Okay, if we look here, we talked about R square earlier. Okay, so R square here equals to 0.5347. Okay, this means that approximately 53% of the variation in home market values can be explained by the home size, okay, by the square feet. The remaining variation could be due to other factors that were not included in this particular model. The standard error, okay, of 7,287 is less than the standard deviation of 10,553. Okay, the value of standard deviation is not shown in this table. This is because the independent variable in the regression model explains some of the variation that we can